Time is an abstraction, a concept that humanity has spent millennia trying to measure and control. From sundials to pendulum clocks, from mechanical gears to the quartz crystals that power modern wristwatches, every device we have ever used to track time has been a tool to approximate something far more elusive. But as technology advanced, we discovered that our traditional methods of measuring time were flawed. They relied on mechanics, on motion, on systems that could be altered by gravity, wear, or environmental factors. They were good, but they were never perfect. Perfection, as it turns out, was not something we had to build. It was something that had existed all along, hidden within the heart of the universe itself, inside the atoms that form the foundation of reality. And among all the elements in existence, one proved to be the ultimate timekeeper: cesium. Cesium-133, a soft, silvery gold metal with unusual properties, became the cornerstone of atomic timekeeping for one reason: it vibrates at a constant, unchanging frequency. It is the heartbeat of time itself, a rhythm so precise that it became the foundation upon which all modern timekeeping is built. When a cesium atom is exposed to energy, it oscillates between two energy states at a frequency of exactly 9,192,631,770 times per second. This number, though oddly specific, is not arbitrary. It is the definition of the second itself. In other words, time does not dictate how an atom moves. Rather, an atom's movement defines what we call time. This realization was groundbreaking. It meant that for the first time in human history, we had a way to measure time that was not based on the movement of celestial bodies or the mechanics of human invention. It was a universal truth, something that would remain unchanged no matter where in the universe it was observed. A second would be a second on Earth, on the Moon, in deep space, or in a distant galaxy, because cesium-133 does not change. To understand why cesium was chosen over other elements, we must first understand how atomic timekeeping works. Atoms are not static. They exist in a constant state of motion, their electrons shifting between energy levels in response to electromagnetic forces. This movement is predictable and, crucially, measurable. When an atom absorbs just the right amount of energy, its electrons transition from one state to another. In cesium-133, this transition is incredibly stable. Unlike other elements, which may have more variable energy states, cesium's resonance is remarkably consistent. Other elements were considered for atomic clocks: rubidium, hydrogen, and even strontium, but none had the same level of reliability and predictability as cesium. Hydrogen masers, for example, are sometimes used in highly specialized atomic clocks, but their frequency stability is slightly less reliable over long periods. Strontium clocks, operating on optical frequencies, have the potential to be even more precise than cesium, but they are far more difficult to maintain. Cesium, with its unique balance of stability and practical usability, became the international standard. This breakthrough led to the creation of the first atomic clock in 1949 at the National Bureau of Standards, though it was not yet as precise as modern versions. By 1955, a cesium-based atomic clock built in England had become so accurate that it was used to redefine the second. The international scientific community adopted this new definition, replacing the old astronomical definition that had been based on Earth's rotation. The difference between an atomic second and a second based on planetary motion may seem trivial, but over time the errors accumulate. The Earth does not rotate at a perfectly constant speed. Its motion is affected by gravitational interactions with the Moon, the drift of its molten core, and even the melting of glaciers. The length of a day, measured in solar time, is gradually changing, imperceptible to humans, but significant when precision matters. The cesium standard removed this uncertainty. With atomic clocks, we no longer relied on an imperfect celestial body to define something as fundamental as a second. Instead, time itself was rooted in something more absolute: the laws of physics. Today, atomic clocks are so precise that they lose only 1 second every 100 million years. That level of accuracy is almost beyond comprehension. To put it another way, if an atomic clock had started ticking at the dawn of the dinosaurs, it would only now be a fraction of a second off. This level of precision is not just an academic achievement, it is essential to the modern world. The Global Positioning System, GPS, a network of satellites orbiting the Earth, depends entirely on atomic timekeeping. Each GPS satellite carries an atomic clock, and the system calculates locations by measuring the time it takes for signals to travel from satellites to receivers on Earth. Because these signals move at the speed of light, even the smallest discrepancy in time, nanoseconds, would cause navigation errors spanning miles. Without atomic clocks, GPS would be useless. Beyond navigation, atomic timekeeping is critical in high-frequency trading, where financial transactions occur in fractions of a second, and in telecommunications, where data synchronization ensures smooth global communications. Scientific research, particularly in fields such as quantum mechanics and astrophysics, also relies on atomic timekeeping to conduct precise experiments and measurements. Despite their remarkable accuracy, atomic clocks must still be corrected periodically. The problem is not with the clocks themselves, but with the fact that Earth's rotation is not as reliable as atomic time. To account for this, scientists occasionally add a leap second to Coordinated Universal Time, UTC, to keep atomic time in sync with planetary motion. These adjustments may seem insignificant, but they have sparked debates among scientists, engineers, and policymakers. Some argue that leap seconds are unnecessary in a world increasingly governed by atomic time, while others insist that keeping atomic time in sync with the astronomical world maintains a deeper connection to natural cycles. Looking to the future, researchers are now developing optical lattice clocks, which use elements like ytterbium and strontium to measure time even more accurately than cesium. These next-generation atomic clocks operate at optical frequencies rather than microwave frequencies, allowing for even finer measurements. If perfected, they could redefine the second once again, making timekeeping even more precise. But the question remains, if we can measure time with near-perfect accuracy, do we truly understand it? We know that atomic oscillations are stable and measurable, but do they reveal the fundamental nature of time? Or are they simply a tool for measuring something deeper? As we continue refining our ability to track time, we must confront a larger question, one that has puzzled scientists and philosophers for centuries. If time is something we measure by atomic motion, then what happens when that motion ceases? If atoms truly define time, does time itself come to an end when the last atom stops vibrating? Or is there something more, something beyond our ability to observe, something that dictates time even in the absence of matter? These questions lead us into the deeper mysteries of time, where the certainty of atomic motion begins to collide with the strange distortions of gravity and space. If time is dictated by the oscillations of cesium, then why does time move differently in different places? If time is truly constant, then why does it slow near a black hole? And if atoms define time, why does time itself seem to slip through our fingers, changing as we age, warping under extreme conditions, bending but never breaking? To answer these questions, we must venture beyond the steady ticking of atomic clocks and into the realm of Einstein's relativity, where time is not an absolute, but a shifting, flowing force that bends under the weight of gravity itself. Time, as we experience it, feels like an unstoppable force, one that marches forward at a steady pace, ticking away in perfect, predictable increments. But what if that isn't true? What if time is not constant at all? What if the very thing we take for granted, the rhythm that defines our lives, is something that can be stretched, compressed, or even stopped altogether? The universe is not bound by the rigid structure of human-made clocks. Time itself bends and distorts under the right conditions, and nowhere is this more evident than in the presence of gravity. More than a century ago, Albert Einstein proposed something radical, something that defied everything we once thought we knew about time. His theory of general relativity suggested that time was not a separate, independent force, but something woven into the very fabric of the universe. Time and space are not two distinct entities. They are one. And that means time can be warped. For most of history, people assumed that time was absolute, that a second was a second no matter where you were. But Einstein's equations shattered that idea. He showed that time is relative, that it moves differently depending on where you are in the universe. More importantly, he showed that the flow of time is directly linked to gravity. The stronger the gravitational field, the slower time moves. This idea is not just a theoretical curiosity, it is a proven fact, something that has been tested and confirmed countless times. Atomic clocks on Earth tick at a slightly different rate than those in orbit. If you were to place one atomic clock at sea level and another on top of a mountain, the two would fall out of sync. The clock closer to Earth's massive gravitational pull would run slower than the one farther away. The effect is small, measurable only in nanoseconds over a long period, but it is real. This phenomenon is known as gravitational time dilation, and while it may seem subtle on Earth, it becomes extreme near the most powerful objects in the cosmos. The closer you are to a massive gravitational force, the more time slows down. And nowhere is this effect more dramatic than near a black hole. A black hole is an object so massive that its gravity is inescapable. Anything that crosses its boundary, the event horizon, is lost forever. But what happens to time near a black hole? According to Einstein, time does something truly bizarre. It begins to stretch. Imagine an astronaut falling toward a black hole. To that astronaut, time would seem to flow normally. Their clock would continue ticking, their heartbeat would continue its rhythm, and they would experience time as they always had. But to an observer watching from a safe distance, something else would happen. The astronaut's movement would appear to slow down. As they reached the event horizon, their motions would become infinitely slow, as if time itself had frozen. If we could somehow place an atomic clock near the edge of a black hole, we would see the same effect. The clock's ticking would slow to a crawl, appearing to nearly stop from the perspective of an outside observer. And yet for someone near the black hole, time would continue as normal. This isn't just a wild thought experiment. We see real-world evidence of gravitational time dilation in action. When we look at the light coming from supermassive black holes, we can measure how the time around them slows. The light is stretched into longer wavelengths, appearing redder than it should be, a phenomenon known as gravitational redshift. This is not just a trick of perspective. It is time itself being distorted by the immense pull of gravity. This effect also means that someone orbiting a black hole at a safe distance could experience time differently from the rest of the universe. If you were to spend a few hours near the event horizon of a supermassive black hole, assuming you could survive, you might return to find that millions of years had passed elsewhere in the universe. This idea was famously portrayed in the film Interstellar, where astronauts experience only minutes near a black hole, while decades pass for those waiting for them. While Hollywood takes creative liberties, the underlying science is accurate. Time really does slow down under strong gravitational fields. But if gravity can stretch time, can it also stop it completely? Einstein's equations suggest that inside a black hole, time comes to an absolute halt. If you were to fall beyond the event horizon, time would cease to have any meaning. There would be no next second, no ticking of a clock. Everything would exist as a frozen moment, forever trapped beyond the reach of the universe. But if time can stop in one part of the universe while continuing elsewhere, then what does that mean for the nature of time itself? Some physicists argue that this suggests time is not fundamental, that it is something that emerges from deeper physical processes. Others believe that time does not actually stop inside a black hole, but instead becomes something else entirely, something we do not yet understand. Could time loop? Could it reverse? Could it fragment into multiple realities? These are questions that remain unanswered. Gravitational time dilation has also forced us to reconsider how we think about the beginning of time itself. When we look at the Big Bang, we are looking at a moment when the entire universe was compressed into a tiny, infinitely dense state. If gravity slows time, then what does that mean for the earliest moments of the cosmos? Some physicists believe that time itself may have been moving infinitely slowly at the birth of the universe, meaning that from our perspective today, the Big Bang may still be unfolding at some deeper cosmic level. These ideas stretch the limits of our understanding, but they also point to something even more unsettling. If time can be stretched, slowed, or even stopped, then what exactly is it? Is it a real, tangible thing? Or is it merely a consequence of motion and gravity? If two people can experience different flows of time simply by being in different places, then whose time is the real time? These are the questions that challenge everything we think we know. They push us beyond the simple ticking of a clock and force us to confront the deeper mysteries of existence. We have measured time with atomic precision, but we have not yet mastered its secrets. And that leads us to perhaps the greatest mystery of all, the nature of time at the smallest scales of the universe. If time can be distorted by gravity, what happens when we look at time in the quantum realm? If a clock can slow down near a black hole, what happens when we observe the ticking of time inside the atom itself? Does time behave the same way at the quantum level? Or does it break down entirely, becoming something else, something more alien than we can imagine? To understand this, we must turn away from the vast scales of black holes and deep space and look inward to the smallest building blocks of the universe. Because as strange as time is in the presence of gravity, it is even stranger when viewed through the lens of quantum mechanics. The world of the very small is unlike anything we experience in everyday life. Atoms, electrons, and subatomic particles do not follow the same rules as the objects we see around us. They do not move in predictable classical ways. Instead, they exist in a strange realm of uncertainty, where position, motion, and even time itself become fluid. If the laws of gravity stretch time on a cosmic scale, then quantum mechanics shatters our understanding of it altogether. For most of human history, time was considered a simple, linear progression. A second follows a second, a minute follows a minute, always moving forward. But as scientists began studying the quantum world, they discovered something deeply unsettling. Time, at the smallest scales of reality, does not behave in the way we expect. One of the most disturbing discoveries in quantum physics is that particles do not have definite positions or velocities until they are observed. This is known as the principle of superposition. A particle, such as an electron, can exist in multiple states at once, moving forward and backward in time, existing in different places simultaneously, until it is measured. Only at the moment of observation does the particle's reality become fixed. If time were an unshakable fundamental property of the universe, this should not be possible. And yet, experiments continue to confirm this bizarre behavior. Perhaps the most famous experiment illustrating this is the double-slit experiment. When particles, such as electrons or photons, are fired through two slits onto a detector, they do not behave like tiny bullets. Instead, they create an interference pattern, as if they are waves passing through both slits at the same time. But when a measuring device is placed to observe which slit the particle goes through, the interference pattern disappears. The particle behaves as if it only passed through one slit. Somehow, the mere act of measurement collapses all the possible futures into a single outcome. This suggests that time, like position and movement, may not be fixed at all. It may be something that emerges only when it is observed. This idea is pushed even further in the Wheeler's delayed choice experiment, an extension of the double-slit experiment. In this experiment, a photon's behavior is determined not at the moment it passes through a slit, but later, when it is measured. This implies that the photon's decision about how to behave is not made in the past, but in the future. If time worked the way we assume, this should be impossible. Cause should always precede effect. But in the quantum world, effect can dictate cause. This leads to one of the most controversial ideas in physics: retrocausality. If quantum events can be influenced by future measurements, does this mean the future can affect the past? Could an event that has not yet happened dictate the behavior of particles in the present? If so, what does that say about time itself? Is it truly moving forward, or are past and future intertwined in ways we cannot yet understand? Quantum entanglement adds another layer of mystery to the nature of time. When two particles become entangled, they share a connection that is instantaneous, no matter how far apart they are. If the state of one particle is changed, the other particle's state will change instantly, even if they are separated by vast distances. Einstein famously called this spooky action at a distance, because it seemed to violate everything we know about time and space. Information should not be able to travel faster than the speed of light, and yet entanglement suggests that some kind of connection exists outside of time itself. This raises profound questions. If two entangled particles remain connected across any distance, does this mean that time does not exist between them? If time were truly a fundamental part of reality, should it not dictate the speed at which information can travel? Entanglement seems to suggest that time is not the rigid structure we believe it to be, but something far stranger, something that can be bypassed, ignored, or even erased under the right conditions. If time does not behave in a strict, linear fashion at the quantum level, then what does this mean for our understanding of time in the larger universe? Could time, like space, be an illusion, something that only emerges when viewed from the right perspective? Some physicists believe that time may not be a fundamental property of reality at all, but rather something that emerges from the interactions of particles and forces. In this view, time is not something that flows like a river, but rather something that arises out of the complex relationships between particles. Without change, without movement, time would have no meaning. If all the particles in the universe were frozen in place, would time still exist? One theory that attempts to reconcile quantum mechanics with the nature of time is the many worlds interpretation. In this view, every possible quantum outcome does not simply collapse into one reality, but instead branches off into a separate universe. Every time a quantum event occurs, the universe splits into multiple parallel realities. In one version of reality, a photon behaves like a wave. In another, it behaves like a particle. Both outcomes exist, but in separate universes. If this theory is correct, then time as we perceive it is an illusion. Every possible version of the past, present, and future exists simultaneously, but we only experience one branch. If time is an illusion created by quantum mechanics, then could it be possible to move through different branches of time? If every possible timeline exists, could we one day find a way to jump from one to another? Could time travel be possible not in the way science fiction imagines it, but in a way dictated by quantum mechanics? If reality is a branching structure of multiple timelines, then what we call time travel may simply be movement through the landscape of probability. Yet, there remains one major problem. While quantum mechanics allows for the possibility of time moving in multiple directions, the universe as a whole seems to insist on a forward direction. This is known as the arrow of time, and it is defined by entropy, the tendency for disorder to increase over time. A broken glass does not spontaneously reassemble. A cup of coffee does not unstir itself. These events only happen in one direction. If quantum mechanics allows for time to be fluid, then why does the universe seem to demand that time moves forward? This paradox is one of the great unanswered questions in physics. The laws of quantum mechanics say time can be reversed, but the laws of thermodynamics say time can only move forward. Somewhere between the quantum world and the macroscopic world, something happens that locks time into a single direction. We do not yet know what that mechanism is. This conflict between the two scales of physics, between the unpredictability of quantum mechanics and the order of classical physics, is at the heart of our greatest scientific mystery. We can measure time with the precision of atomic clocks, but we cannot yet explain why time behaves the way it does. We can slow time near black holes, but we cannot say why it flows at all. We can manipulate quantum particles across time, but we cannot yet understand what time truly is. As we move forward in our understanding, we may be forced to accept a reality that is more bizarre than anything we imagined. If time is not fundamental, if it is merely an emergent property of matter and energy, then what does that mean for us? Are we moving forward in time, or are we simply experiencing one possible version of reality out of an infinite number? And if time is an illusion, then what lies beyond it? To answer this, we must turn to the deeper question of whether time itself is real or simply a trick of our perception. If time can be bent by gravity, manipulated at the quantum level, and even reversed in equations, then is time a force of nature, or is it something we impose upon the universe? This leads to the most unsettling question of all. Does time exist at all? The concept of time is something we take for granted. It moves forward, dragging everything with it. We experience its effects every moment of our lives, and yet, despite our ability to measure time with atomic precision, we still do not fully understand what it actually is. This question becomes even more troubling when we begin to consider the possibility that time may not exist in any real, fundamental way. One of the most unsettling ideas in modern physics is that time may not be a fundamental property of the universe at all. Instead, it may be something that emerges from deeper, underlying physical processes. In this view, time is not a thing that flows independently of the universe, but a consequence of the interactions between particles, energy, and space. This concept challenges everything we assume about reality. If time is not fundamental, then what exactly are we experiencing? Some physicists argue that time is nothing more than a byproduct of entropy, the gradual increase of disorder in the universe. In this view, time does not truly exist as an independent force. It is simply a way to describe how things change. When a cup of hot coffee cools down, when a candle burns, when a star explodes, these are all changes in the arrangement of matter and energy. We perceive these changes as time passing, but in reality, we are simply witnessing entropy increasing. This idea is known as the thermodynamic arrow of time. It suggests that time moves forward only because the universe is becoming more disordered. If time were truly fundamental, then there should be no reason it cannot move backward as easily as it moves forward, and yet we never see broken glasses reassemble themselves or smoke return to a fire. Everything in the universe moves toward greater disorder, and we call that movement time. But if time is just entropy, then does time exist in places where entropy does not change? What happens inside a black hole, where all motion is crushed into a single point? What happens in the vacuum of space, where the laws of thermodynamics break down? If entropy is the only thing driving time forward, then does time cease to exist in regions where entropy is constant? This question becomes even more disturbing when we consider the heat death of the universe. If the universe continues expanding, then one day, trillions of years from now, all energy will be evenly spread out, and no further changes will occur. There will be no stars, no planets, no motion, only a cold, empty void. In such a state, entropy will reach its maximum, and nothing will be able to change. If nothing can change, then time will have no meaning. If time is simply the measure of change, then when change stops, does time itself stop as well? This idea suggests a terrifying possibility. Time may not be eternal. It may have had a beginning, and it may have an end. If time is an emergent property of matter and energy, then before the universe existed, time did not exist either, and if the universe reaches a final, motionless state, then time may cease to exist in the future as well. In this view, time is not an infinite river flowing forever. It is a temporary phenomenon, something that appeared when the universe began, and will vanish when the universe fades away. Some scientists propose an even stranger idea, that all of time, past, present, and future, already exists simultaneously. This is known as the block universe theory. In this view, time is like a book, with every page already written. We experience time as if we are reading the book one page at a time, but in reality the entire book exists at once. Every moment that has ever happened and ever will happen is already there. We simply experience it in a linear sequence because that is how our brains interpret reality. This idea is deeply unsettling because it suggests that the future is already set. If time is a fixed structure, then what we call free will may be an illusion. Every decision we make, every action we take, may have already been determined. The past, the present, and the future are all equally real, and we are merely traveling through them. This conflicts with our everyday experience. We feel as though we are making choices, shaping the future moment by moment. But if the block universe theory is correct, then the future is just as unchangeable as the past. Our experience of time moving forward may simply be a trick of perception, a result of the way our brains process information. But if time is already set, then why do we experience it as flowing? The answer may lie in the way our consciousness interacts with reality. Some scientists believe that our perception of time is linked to how our brains process memories. The past exists in our minds as memories, the present as immediate experience, and the future as an expectation. But this does not mean that time itself is actually moving. It may simply mean that our awareness is moving through time, like a flashlight illuminating different parts of a dark room. Another explanation comes from quantum mechanics. In the quantum world, events do not unfold in a strict linear sequence. Particles can exist in multiple states at once, only collapsing into a definite state when observed. This suggests that time, like position and motion, may not be an objective feature of the universe, but something that emerges when an observer interacts with it. In other words, time may not exist independently of our perception. If this is true, then what we call time may not be something out there in the universe, but something created by our minds. Our consciousness may be imposing a structure on reality that does not actually exist. If our perception of time is an illusion, then what does that say about our existence? Are we living in a reality that is far stranger than we realize? Are we simply trapped in a system of perception that forces us to experience the universe in a way that does not reflect its true nature? If time does not exist as we believe it does, then what does that mean for our place in the universe? Are we moving through time, or are we simply experiencing different points of an unchanging reality? If the future is already set, then can we ever truly change anything? And if time is just a temporary phenomenon, something that appeared when the universe was born and will vanish when it dies, then what happens when time finally runs out? These are the questions that challenge everything we think we know. They force us to reconsider not just the nature of time, but the nature of reality itself. If time is not fundamental, then what else about our existence is an illusion? If the flow of time is something our minds create, then what happens when we reach the end of the line? As we approach the limits of our understanding, we must confront the possibility that time, as we experience it, is nothing more than a shadow of something deeper, something beyond our ability to perceive. And if that is the case, then what lies beyond time itself? The concept of time has always been deeply connected to human experience. We wake, we work, we age, and eventually we pass on, all under the unrelenting march of time. Every aspect of our reality is governed by its passage. But what if time is not what we think it is? What if it is not the river flowing steadily forward, but something far stranger? Something woven into the very structure of space itself? The idea that time is an independent force, moving forward in a straight line, is an illusion born out of human perception. In truth, time does not exist separately from space. The two are bound together into what physicists call space-time, a single fabric that stretches across the universe. What we call time is simply one dimension of that fabric, no different from the dimensions of width, height, and depth. We experience time as moving forward because that is how we are built to perceive it. But time does not move in any real sense. It is simply there, a fixed dimension of the cosmos. This concept, introduced by Einstein, shattered everything we once thought we knew. Time is not an external clock ticking away, it is part of the structure of reality itself. But if time and space are one and the same, then time is not absolute. It can stretch, it can compress, and under the right conditions, it can even come to a complete stop. We see the effects of this in extreme environments, such as the warped space around black holes. We have already explored how gravity slows time, but the full implications of this phenomenon are even more unsettling. If time can be stretched, then what does that say about the past and the future? If time is part of space, then is the past still there somewhere, just as a distant galaxy is still there in space? Is the future already written, simply waiting for us to arrive? This leads to one of the most troubling implications of modern physics, the possibility that the past, present, and future all exist simultaneously. In this view, time does not flow at all. Instead, every moment that has ever happened, and every moment that ever will happen, already exists. We simply experience these moments in a sequence. Just as we can move through space, some theories suggest that it might be possible to move through time as well, not in the way that science fiction imagines, but in a way dictated by the underlying structure of space-time. If this is true, then what we call now is merely an illusion, a single point in a vast, unchanging structure. Every event that has ever occurred and every event that ever will occur is already there, fixed in place. We are not moving through time. We are simply experiencing different slices of an already existing reality. But if time is fixed, then why do we experience it as flowing forward? The answer may lie in a strange phenomenon known as the arrow of time. In physics, almost every fundamental law is time reversible. In other words, if you were to run the equations of motion backward, they would still make sense. A planet orbiting a star follows the same mathematical laws, whether time moves forward or backward. The laws of quantum mechanics, gravity, and electromagnetism do not require time to have a preferred direction. And yet, in our experience, time always moves forward. We remember the past, but we do not remember the future. Why? The answer appears to be entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases over time. A glass shatters, but it never unshatters. A candle burns, but it never reforms from smoke and wax. Heat flows from a hot object to a cold one, but never in reverse. This is the one law of physics that is not time symmetrical. It tells us that time has a direction, that it moves from a state of low entropy to high entropy. But why does the universe obey this rule? One possible explanation is that the universe began in an extremely low entropy state. At the moment of the Big Bang, the cosmos was in an ordered, compact, and structured form. Over time, as the universe expanded, disorder increased. This initial condition may be the reason we experience time as flowing forward, because the universe is moving toward a state of greater entropy. But this explanation leads to another troubling question. If time's direction is simply a consequence of entropy, then what happens when the universe reaches its final state of disorder? In one possible future, the universe continues expanding indefinitely. Over trillions of years, stars burn out, galaxies drift apart, and all matter is eventually swallowed by black holes. Over even longer timescales, those black holes evaporate, leaving behind only a thin, cold mist of particles spread across an empty void. This is known as the heat death of the universe. If entropy is what drives time forward, then in this final state of complete disorder, time itself would cease to have meaning. with no energy to create change, with no events left to unfold, what would it even mean to say that time still exists? This raises an even more disturbing possibility. If the flow of time is nothing more than the march of entropy, then could it be possible for time to run in reverse? If the universe were to somehow return to a lower entropy state, would time move backward? Would we unlive our lives, growing younger instead of older, watching the world rewind? While this may seem impossible, there are some theories that suggest that, at the farthest edges of the cosmos, time may already be behaving in ways we do not yet understand. One such theory suggests that on the other side of the Big Bang, time may have flowed in reverse. In this view, our universe is just one half of a larger symmetrical reality, with time moving forward in one direction in our cosmos and backward in the other. To an observer in that mirrored universe, we would appear to be moving in reverse, just as they would appear to us to be doing the same. In this model, the beginning of time as we know it is simply the middle of a much larger, more complex structure. If this is true, then time is not a straight line but a cycle, a loop that bends back on itself. The end of the universe may not be the final death of time, but simply the beginning of another cosmic age. This idea, known as the cyclic universe theory, suggests that time is not something that flows eternally in one direction, but something that resets, repeating endlessly in a grand cosmic dance. But even if this theory is true, it still does not answer the most fundamental question of all. Why does time exist in the first place? Is time truly a fundamental feature of the universe, or is it just a human construct, something we impose on reality to make sense of our experiences? If time is simply a property of space, then does it exist independently, or is it created by the way we interact with the universe? Could it be that, outside of human perception, time is something far stranger than we can comprehend? As we continue to explore the nature of time, we find ourselves confronted with ever more unsettling questions. We can measure time with atomic precision, but we still do not fully understand why it moves forward. We can slow time with gravity, but we do not know if it can ever truly be stopped. We can describe time in mathematical terms, but we cannot say for certain whether it exists as a real thing or merely as an illusion of human consciousness. And yet, despite all of these mysteries, one thing remains certain. Whether time is real or an illusion, whether it flows eternally or is bound to a cycle, whether it is fundamental or emergent, we are all subject to its passage. We may not understand time, but we live within it. It defines our existence, shaping every moment of our lives. The final question, then, is not what time is, but what it means. If time is real, then what lies beyond it? If time is an illusion, then what is the true nature of reality? If time is part of the universe, then what happens when the universe ends? These are the questions that remain, questions that will continue to challenge scientists, philosophers, and thinkers for generations to come. And perhaps in the end, time itself will be the only thing that holds the answers. The future of time is one of the greatest unknowns in science. We can measure it with atomic precision, we can manipulate it with gravity, and we can theorize about its origins, but we have yet to answer the ultimate question: will we ever control it? Throughout history, time has been something we could only observe and measure, never something we could change. But as our understanding of physics grows, the possibility of altering time in fundamental ways no longer seems like mere science fiction. Theoretical physics suggests that time is flexible, not rigid. Under the right conditions, time can slow, stop, or even loop back on itself. If time is a physical dimension, then in theory it should be possible to move through it just as we move through space. This raises the question, could we ever develop the technology to manipulate time itself? The closest thing we have to a real-world time machine is Einstein's theory of relativity. We already know that time moves slower in stronger gravitational fields and at higher speeds. This means that if someone were to travel close to the speed of light, time for them would slow relative to an observer at rest. This is known as time dilation, and it has been confirmed through real-world experiments using atomic clocks on high-speed aircraft and satellites. If a spacecraft could reach near-light speeds, the people inside would age much more slowly than those left behind on Earth. A journey that felt like just a few years to the traveler could result in centuries passing back home. In this sense, time travel into the future is not only possible, but has already been demonstrated in small ways. The real challenge is whether time travel to the past is possible. The laws of physics do not explicitly forbid it, but they create massive obstacles. One of the most famous proposals for backward time travel is the concept of a traversable wormhole. A wormhole is a theoretical tunnel through space-time, connecting two distant points through a shortcut. If one end of the wormhole was placed near a massive gravitational source, like a black hole, and the other end was moved at relativistic speeds, time dilation could cause a difference in the rate of time passing at each entrance. In theory, this could allow a traveler to step into one end of the wormhole and emerge at an earlier time through the other end. The problem is that wormholes, if they exist at all, are incredibly unstable. Any attempt to travel through one might cause it to collapse, crushing anything inside. Even if we could stabilize a wormhole, there is no evidence that it would allow travel to the past in a way that preserves causality. The famous grandfather paradox illustrates the problem. If you travel to the past and prevent your own existence, then how could you have traveled to the past in the first place? Some physicists suggest that nature has a built-in protection against time travel paradoxes. The Novikov self-consistency principle states that if time travel to the past is possible, then any events that occur must be consistent with history. In other words, even if you travel back in time, you cannot change events in a way that would create contradictions. Everything you do would have already happened. You might think you are altering the past, but in reality, you would be fulfilling it. This suggests that if backward time travel ever becomes possible, it may work in a way that prevents free will from altering historical events. There is also the idea that time travel does not allow for a single timeline to be altered, but instead creates a branching effect, forming multiple realities. This concept is explored in the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of an event happens in separate parallel universes. If this is true, then time travelers would not be changing their own past, but instead creating a new timeline that diverges from the one they left. In this view, every moment of decision creates a new universe, each existing independently of the others. But even if time travel proves to be impossible in the traditional sense, that does not mean we will never find ways to manipulate time on a smaller scale. The discovery of quantum time effects suggests that time may not be as rigid as we once thought. In recent years, scientists have demonstrated the ability to reverse the state of quantum particles, effectively creating a form of time reversal at a microscopic level. These experiments do not yet allow for anything as dramatic as sending a human being through time, but they indicate that the flow of time may not be as fixed as it appears. Another avenue for controlling time may come from understanding the relationship between time and consciousness. Our perception of time is deeply tied to the way our brains process information. Certain experiences, such as intense fear or near-death situations, can make time seem to slow down, while periods of deep focus can cause hours to pass in what feels like minutes. If time, as we experience it, is partly a function of consciousness, then could we one day develop technologies that alter our perception of time? Could we artificially slow down or speed up our internal clocks, allowing us to extend subjective moments or compress long stretches of time into brief experiences? Some futurists speculate that as we develop more advanced forms of artificial intelligence and neural interfaces, we may find ways to separate our perception of time from the constraints of biological aging. If a human mind could be uploaded into a digital system, would that mind still experience time in the same way? Could a conscious being, freed from a biological body, slow down or speed up its subjective experience of time at will? If so, then time, as it applies to human experience, could become something malleable, something that can be shaped by individual choice rather than external forces. These questions lead to an even greater mystery. If we could control time, should we? The ability to manipulate time, even in small ways, would have profound consequences. If time travel were possible, would it be safe? Would it be ethical? If people could extend their lives indefinitely by slowing down their personal experience of time, what impact would that have on society? Would time itself become a form of currency, something that could be bought and sold? Would we create entire societies that exist on different timescales, where one group of people experiences the world at a vastly different speed than another? The idea of controlling time raises as many dangers as it does possibilities. If time travel were ever to be developed, it could be weaponized, creating catastrophic consequences for the fabric of reality. Even if we could only slow or speed up time, the ability to alter time perception could lead to unforeseen psychological and social effects. The more we understand time, the more we realize that it is not just an abstract concept. It is the very foundation upon which reality is built. Despite all these unknowns, one thing is clear. The future of time is not just a question of physics, but of philosophy, ethics, and the nature of human existence itself. We are moving toward an era where time may no longer be something we simply measure, but something we can, in some way, influence. Whether through advances in relativity, quantum mechanics, or even consciousness itself, our understanding of time is evolving. But as we explore these possibilities, we must also confront the limits of our own perception. Are we truly on the verge of mastering time? Or are we simply uncovering deeper mysteries that we are not yet equipped to understand? And if we do one day gain control over time, what will we do with it? Will we use it to explore the cosmos, to extend our lives, or to unlock hidden truths about the universe? Or will we discover that time, once understood, is something that should never be tampered with? The future of time is unknown. But the fact that we are even asking these questions suggests that we are on the edge of something profound. And as we move forward into the great unknown, we may find that time is not just something we live within, but something that, in the deepest sense, defines us. The ultimate fate of time itself is one of the greatest unresolved mysteries in physics. We have measured time with atomic precision, observed its distortions near black holes, and questioned whether it even exists as we perceive it. But one question still lingers. Will time ever run out? The universe has a beginning. Most scientists agree that time, as we experience it, started with the Big Bang roughly 13.8 billion years ago. Before that moment, if there even was a before, time did not exist in any meaningful way. Space, energy, and matter exploded outward from a singularity, setting in motion the expansion of the cosmos. But if time had a beginning, does it also have an end? One possibility is that time will continue indefinitely, stretching on forever as the universe expands. But this depends on what happens to the universe itself. If the cosmos has a finite lifespan, then so does time. The ultimate fate of time is linked to the fate of the universe, and there are several competing theories about how it could all come to an end. The most widely accepted scenario is known as the heat death of the universe. This idea is based on the second law of thermodynamics, which states that entropy, the measure of disorder, always increases over time. Stars burn their fuel, galaxies drift apart, and the energy available to do work slowly diminishes. If this trend continues indefinitely, then the universe will eventually reach a state of maximum entropy. At this point, no new stars will form, no chemical reactions will take place, and no life will be able to exist. The universe will become a cold, dark void where nothing changes. If change is what defines time, then in this final state, time itself may effectively stop. This is not a dramatic, sudden end. It is a slow, inevitable decline into nothingness, a process that could take trillions upon trillions of years. Long before the final embers of the last stars fade, black holes will dominate the universe, consuming any remaining matter. Eventually, even black holes will evaporate due to Hawking radiation, leaving behind only stray particles and the faint glow of background radiation. With no processes left to mark its passage, what would time even mean in such a universe? If nothing happens, does time still exist? Another possibility is the Big Crunch. If the force of gravity overcomes the expansion of the universe, then at some point the cosmos could begin to contract instead of expand. Galaxies would draw closer together, temperatures would rise, and the entire universe would collapse back into a singularity, much like the moment of the Big Bang in reverse. If this happens, then time, as we know it, would cease to exist. It would have a definite end, just as it had a beginning. Some theorists suggest that this could lead to a cyclic model of the universe, where each big crunch is followed by another Big Bang, endlessly resetting the cosmic clock. In this view, time does not have a single beginning or end, but rather an infinite series of rebirths. A third, more radical theory is known as the Big Rip. If dark energy, the mysterious force driving the accelerated expansion of the universe, continues to grow in strength, it could eventually tear everything apart. First, galaxies would be ripped away from each other, then stars from their planetary systems, then atoms from one another. In the final moments before the fabric of space itself is torn apart, time may cease to have any meaning, as the very structure of reality collapses. This would be the most violent and abrupt end to time, a catastrophic disintegration of everything. But what if time does not have an end in the way we imagine? Some theories suggest that time is an emergent property, something that arises from deeper physical processes. If this is the case, then time may not need to have a defined beginning or end. It may simply be one way in which the universe organizes itself, something that emerges from interactions between matter and energy. In this view, time does not end because it was never fundamental to begin with. Another unsettling possibility is that time could end for us, but not for the universe. If a phenomenon such as vacuum decay were to occur, the universe as we know it could be replaced by a different kind of space-time with entirely different physical laws. In this case, time as we experience it would cease instantly, but something else might continue. There is also the question of whether time exists outside of our universe. If our cosmos is just one of many in a multiverse, then perhaps time is something local to our particular reality. In this case, time might end for us, but in another universe, it could continue or function in an entirely different way. But even if time does have an ultimate endpoint, what does that mean for us? Humans have always been obsessed with time because it is inescapable. We experience time not just on a cosmic scale, but on a deeply personal level. Our lives are defined by it. We measure our existence in years, in moments, in memories. Time is the thing we never have enough of, the force that moves us toward an unknown future. And yet, we still do not fully understand it. If time were to end, would that mean the end of existence itself? Or would it simply mean the end of time as we perceive it? Could we experience a reality beyond time? Is time something that applies only to the physical universe, or is it something deeper? There are those who speculate that consciousness itself might be separate from time. If time is just a feature of the physical world, then could a form of awareness exist outside of it? Some interpretations of quantum mechanics suggest that consciousness plays a role in shaping reality. If that is the case, then what happens when time itself disappears? These are questions that go beyond physics and into the realm of philosophy, perhaps even beyond what science can answer. But they force us to confront something profound. Our understanding of time is still incomplete. No matter which theory turns out to be correct, one thing is certain. Time, whether an illusion or a fundamental aspect of reality, is something we cannot escape. It is woven into everything we do, everything we are. And until we understand its true nature, it will remain one of the greatest mysteries of the universe. So, what happens when time runs out? Perhaps that is the wrong question. Maybe the real question is whether time ever existed at all. The nature of time has long been debated by scientists and philosophers alike, but one question lingers above all others. If time is truly fundamental to the universe, then what happens when it is no longer measurable? If time is something that emerges from physical processes, then what happens when those processes cease? These questions lead to a final and unsettling mystery. What lies beyond time itself? We often think of time as an endless progression, stretching infinitely into the past and the future. But if the universe is finite, then time may be as well. Some physicists propose that time, much like space, could be part of a larger framework of existence, one that is itself bound by deeper laws we do not yet understand. If time is not an absolute but merely a construct, then it raises the question of whether anything can truly be considered eternal. One of the most radical ideas in modern physics is that time may not even exist in any fundamental way. In the field of quantum gravity, some researchers believe that time is not a basic feature of the universe, but an emergent phenomenon, something that arises from the interactions of particles and fields at the most microscopic levels. In this view, the passage of time is not a property of the universe itself, but something we impose on reality in order to make sense of it. This concept is difficult to grasp because our entire existence is structured around time. We experience life as a sequence of moments, each leading to the next. Our memories are arranged in a linear fashion, giving us the impression that time moves in one direction. But what if this is simply a limitation of human consciousness? What if time is not a real thing, but merely a way for our brains to interpret change? Some theories suggest that if we could step outside of time, we would see the entire universe as a single, unchanging structure. Every moment that has ever happened, and every moment that ever will happen, could be seen all at once, like a vast frozen landscape. From this perspective, what we call the past and the future are just different points in an unchanging reality. The only reason we experience time as moving forward is because we are locked into a particular way of perceiving it. If this is true, then what happens when time reaches its end? If time is not fundamental, then it does not need to continue indefinitely. It may simply dissolve, leaving behind a reality that is beyond anything we can currently comprehend. This idea is similar to the way we once thought of the edge of the earth. For most of history, humans believed the world had boundaries, that if you sailed far enough, you would reach the end. But once we understood the nature of the earth as a sphere, we realized that what we had thought of as an edge was merely a misunderstanding of the larger structure. Some physicists believe that time may work the same way. What we perceive as the end of time may simply be the boundary of our understanding, the limit of our perception, rather than an actual conclusion. But even if time is an illusion, we cannot escape the fact that we experience it. It is real to us in every possible way. We measure it, we feel its effects, and we build our lives around it. If time is merely a construct of the human mind, then what happens when human consciousness reaches its own limits? Do we experience something beyond time, or do we simply cease to exist? Some physicists speculate that if time is truly a byproduct of the physical universe, then anything outside of this universe would not be bound by it. If there are other dimensions, other universes, or deeper structures to reality, then they may not be subject to time as we understand it. If consciousness can exist beyond the physical, then it might also exist beyond time. This is an idea that has fascinated thinkers for centuries. Many ancient traditions speak of a realm beyond time, a state of being that is eternal and unchanging. Could it be that modern physics is only now beginning to uncover what ancient philosophies have long hinted at? The search for the true nature of time is ultimately a search for the nature of reality itself. If time is fundamental, then we must discover its ultimate fate. If it is not, then we must ask what reality looks like without it. If time is simply something that emerges from deeper physical processes, then what happens when those processes no longer function? These are not just theoretical questions. They force us to confront our place in the universe. We exist in time, but we do not yet understand why. We measure its passage, but we do not know what it truly is. We experience time moving forward, but we do not know if it moves at all. If time is an illusion, then what does that say about everything we experience? If time is not fundamental, then what is? In the end, the question of what happens when time runs out may not be something we can ever answer. It may be that time, like space, is simply one aspect of a much larger reality, one that we have not yet even begun to comprehend. Perhaps the most unsettling possibility of all is that we will never truly know, that our understanding of time will always be incomplete. And if that is the case, then perhaps the greatest mystery of time is not how it began or how it will end, but whether we were ever meant to understand it in the first place. The mystery of time brings us to the final question. What does it mean for us? Whether time is an illusion, a fundamental property of the universe, or an emergent phenomenon, we cannot escape the fact that it defines our existence. We are beings trapped within time, bound to its forward movement, unable to stop, reverse, or escape its grasp. But if time is not what we think it is, then what does that say about life itself? For centuries, humans have searched for ways to extend time, to slow its passage, to defy aging and death. Ancient civilizations built monuments to endure for eternity, believing they could outlast time itself. Philosophers debated whether time was a force that moved independently or if it was something created by human perception. Scientists developed increasingly accurate ways to measure time, yet still struggled to explain what it actually is. Even today, the search for time travel and longevity are among humanity's most persistent obsessions. But if time is an illusion, then what does it mean to grow old? If time is merely a construct of human consciousness, then what does it mean to experience a lifetime? And if time is something that emerges from the fabric of space, then what happens to us when time itself reaches its end? Some scientists argue that consciousness itself may not be bound by time in the way we assume. If time is a physical property of the universe rather than a fundamental force, then what happens to awareness when the body is no longer subject to its effects? Could consciousness exist outside of time? Quantum mechanics has already demonstrated that at the smallest scales, time behaves in ways that defy logic. Particles do not follow a strict past-to-future sequence. They exist in multiple states at once until observed. If consciousness operates on principles we do not yet understand, then could it too be untethered from time? Could our experience of time be something imposed upon us by our physical form, rather than something intrinsic to our awareness? This question takes us beyond physics and into philosophy. If time is simply the way we experience change, then what happens if we reach a state where change is no longer possible? Do we cease to exist, or do we experience something beyond time itself? Some religious and philosophical traditions have long suggested that time is not the ultimate reality. Many belief systems describe an eternal state, where existence is not bound by past, present, or future. Could it be that our scientific understanding of time is only now catching up with an idea that has been present for centuries? Even if we set aside philosophical and metaphysical questions, the nature of time has practical consequences for our future as a species. If we could one day manipulate time, slow it down, extend it, or step outside of it, what would that mean for human civilization? If the flow of time can be altered, then could we one day experience a reality where time is no longer a constraint? Could we develop technology that allows us to exist outside of time as we know it? One of the most exciting possibilities is that time, like space, could be explored. If time is a dimension, then in theory, it may be possible to navigate it. We think of time as something that happens to us, something we cannot control. But what if we could? What if instead of merely living within time, we could learn to move through it, to manipulate it as easily as we manipulate objects in space? The search for time travel continues to push the boundaries of our understanding. We know that time travel into the future is possible through relativistic effects. We know that time can be slowed by gravity and speed. We suspect that wormholes, if they exist, could provide shortcuts through time as well as space. But if the laws of physics allow for the possibility of traveling through time, then what does that mean for free will? If time travel is possible, does that mean the future is already determined? If someone from the future could visit the past, does that mean every event has already happened, locked in place? These questions challenge the very nature of reality. We think of time as something fluid, something in motion. But if time is a structure, then it is already set, unchangeable, existing all at once. If that is the case, then we are not moving through time at all. We are simply experiencing one small portion of a much larger, already existing reality. In the end, the study of time forces us to confront the most fundamental questions about existence itself. Are we beings who move through time, or are we simply conscious observers within a fixed structure? If time is an illusion, then what is real? If time is real, then what happens when it ends? The more we study time, the less we seem to understand it. We have built atomic clocks that measure time with unprecedented precision, yet we do not fully understand what it is we are measuring. We have equations that describe time's behavior, yet we do not know why time moves forward and not backward. We have theories that suggest time is an illusion, yet we cannot explain why we experience it so vividly. Perhaps time is the greatest mystery of all, not because we do not understand it, but because we are part of it. We cannot step outside of time to observe it from a distance. We are inside the mystery, and that may be why we can never truly solve it. But one thing is certain: whether time is fundamental or emergent, whether it will end or continue indefinitely, whether it is something real or an illusion, it remains the defining feature of our reality. It shapes every moment of our lives, every thought, every action. And until we unlock its deepest secrets, time will remain both our greatest limitation and our greatest unanswered question. And so we are left with a final thought. If time is an illusion, it is the most convincing illusion ever created. If time is real, then it is the most mysterious force in existence. Either way, we are its prisoners. At least for now. If time is an illusion, then what does that say about our place in the universe? If time is real, then why does it seem to slip through our fingers like sand? Whether time is fundamental or emergent, real or imagined, linear or cyclical, one thing is clear. It is something we have never been able to escape. We live within its grasp, measuring our lives by its passage, but never fully understanding what it truly is. And yet, despite our inability to control it, time shapes everything we do. This brings us to perhaps the most profound question of all. What does time mean for us? Beyond physics and philosophy, beyond equations and theories, how does time define the human experience? We are born, we grow, we learn, we love, we lose, and ultimately, we vanish, all under the relentless march of time. Every second we live is a second we will never get back. Every moment is both fleeting and permanent, happening once and then becoming part of the past. If time is an illusion, then why does it feel so real? If time is real, then why does it seem so fragile? Time is deeply personal. We measure it not just with clocks, but with memories, with regrets, with hope. We mark it with birthdays, anniversaries, and milestones. We feel it in the aging of our bodies, the fading of our childhood, the loss of those we love. No matter how much we learn about time as a scientific concept, we cannot separate it from our own existence. But what if time is not what we think it is? What if our perception of it is incomplete? Some theories suggest that the passage of time is an illusion created by the way our consciousness interacts with reality. If our brains process information differently, could we experience time in an entirely new way? Some moments seem to last forever, while others disappear in an instant. Could this mean that time is not something external, but something created by our own awareness? If time is truly an illusion, then what happens when we die? Is consciousness tied to time, or could it exist outside of it? Some scientists speculate that if time is merely an emergent property of the universe, then it may not apply to all forms of existence. Could there be something beyond time, something we cannot yet perceive? Could time itself be a construct of human minds, something that only exists because we experience it? And if time is real, then what happens when we reach the end of it? If the universe one day enters a final state, whether through heat, death, collapse, or some other unknown fate, does time simply stop? If time is bound to the physical universe, then does that mean reality itself has an expiration date? Or could there be something beyond time, something that continues even after time itself is no more? These are questions that science has not yet answered. Perhaps they are questions that science will never answer. But what we do know is that time, whether an illusion or a fundamental force, is something we cannot escape. It is the invisible force that moves us forward, the thread that ties our past to our future. It is both the stage and the script, the framework of everything we know. Yet, despite its power over us, time is something we often take for granted. We assume there will always be more of it, that tomorrow will always come, that we will always have another chance. But time is the one thing we can never reclaim. Every moment we live is a moment gone forever. We chase time, we fight against it, we try to slow it down. But in the end, time always wins. And so, perhaps the final lesson of time is not about physics or mathematics, but about how we choose to live. Whether time is real or an illusion, whether it is infinite or finite, whether it will end or continue forever, we have only the time we are given. So what will we do with it? That is the only question that truly matters. Bottom of form. The story of time is not over. It never has been. Whether time is fundamental or an illusion, whether it is a river that carries us forward or an endless landscape we only glimpse one step at a time, one thing is certain: we are only beginning to understand it. For thousands of years, humanity has been obsessed with time. We have built monuments to track its passage, created calendars to organize our lives, and developed the most advanced atomic clocks to measure it down to billionths of a second. Yet despite all of this, the true nature of time remains one of the greatest unsolved mysteries in science. In the coming centuries, we may finally unlock some of its secrets. As our technology advances, as our understanding of the universe deepens, as our exploration of the quantum world and the cosmos expands, we may begin to reshape our relationship with time in ways that today seem impossible. But where will this journey take us? One possibility is that we will discover a way to manipulate time itself. We already know that time is not absolute, that it bends under gravity, slows at high speeds, and behaves unpredictably at the quantum level. It is not impossible to imagine a future where we learn to control these effects. Perhaps one day, we will develop the technology to slow time on demand, allowing us to experience years in what feels like mere moments. Maybe we will extend human lifespans not by altering biology, but by changing the very rate at which time flows for us. Some theorists even speculate that one day we might be able to stop time altogether. If time is an emergent property of the universe, then in theory, we might find a way to remove ourselves from its influence. What would it be like to exist outside of time? Would we be frozen, unable to act or think? Or would we experience something completely beyond human comprehension? Would we become immortal? Or would we cease to be entirely? Then there is the question of time travel. We know that traveling into the future is possible. Astronauts aboard the International Space Station age slightly slower than those on Earth due to relativistic effects. But traveling into the past remains one of the great barriers of physics. Wormholes, closed time-like curves, and quantum paradoxes all suggest that the laws of the universe resist backward time travel. But if time travel to the past is ever proven possible, even in theory, it would change everything. History would no longer be fixed. The past would become something we could visit, perhaps even alter. Would we be responsible enough to handle such power? Could we be trusted with the ability to undo mistakes, to relive moments, to save those we lost? And if time is a fixed structure, as some theories suggest, would we find that we are powerless to change anything? That every attempt to rewrite the past only leads to the same inevitable outcome? Even if time travel is impossible in the physical sense, our perception of time could one day become something entirely different. Advanced AI, brain-computer interfaces, and virtual reality may allow us to manipulate our experience of time, even if we cannot change time itself. If our consciousness could be digitized or uploaded into a different medium, could we exist in a state where time no longer matters? Would we become beings who can perceive all moments at once, or would we find that without time, existence itself becomes meaningless? Beyond human experience, the fate of time is tied to the fate of the universe itself. We have explored the possibilities, the heat-death, the big crunch, the big rip. But what if none of these are the true end? What if time continues in ways we cannot yet imagine? One radical idea suggests that our universe is just one of many, and that time in our universe may have an expiration date, but time itself does not. If the multiverse is real, then other universes may have entirely different structures of time. Some may flow backward, some may loop infinitely, and some may not have time at all. Could it be that time is only a feature of our particular reality, not a fundamental aspect of existence itself? Another possibility is that time is a cycle, an endless repetition of creation and destruction. If the universe collapses and then explodes into a new Big Bang, does that mean time resets? Do we live the same lives over and over without knowing it? Could we already be caught in an infinite loop, experiencing the same universe again and again with no memory of the previous cycle? Or perhaps time itself evolves. Just as life and the universe itself have changed over billions of years, could time itself be undergoing a transformation? Could time, as we know it, be merely a phase, something that will one day be replaced by a new form of reality beyond our comprehension? These are not questions we can answer yet. Perhaps we never will, but they remind us that our understanding of time is still in its infancy. We are like early astronomers looking at the stars, unaware of galaxies beyond our own. We have uncovered glimpses of the truth, but we have yet to see the full picture. What we do know is that time, whether real or an illusion, has shaped everything we are. It has given us history, memory, and meaning. It has driven us to create, to explore, to wonder. It has defined our existence and will continue to do so, even as we push further into the unknown. And so, as we look ahead to the future, we must ask ourselves, what will we do with the time we have left? Whether that time is finite or infinite, whether it is a universal constant or an illusion of human perception, it is all we have. Every moment is fleeting, but every moment is also eternal, in the sense that once it has happened, it can never be undone. So perhaps, in the end, the greatest lesson of time is not about physics or space, or the universe itself. Perhaps the greatest lesson of time is that it forces us to live, to make choices, to experience, to leave behind something that matters. Time may one day end. The universe may one day fall silent. But as long as time exists, as long as we exist within it, we must use it well. Because if time is the most valuable thing in the universe, then what we do with it is the only thing that truly matters. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.